Alright, so today's lesson is on the standard model of particle physics. I'm just going to go over all of the fundamental particles of nature that we know of. Now, protons and neutrons are not fundamental particles. They're made up of quarks, and quarks are fundamental particles. Quarks are a particle that make up what we call hadrons. And hadrons are split into mesons and baryons. Okay, the difference between mesons and baryons. Mesons are a combination of one quark and an anti-quark. So if we go down in my handout here, here's some examples of meson. So this is a pion, a pi plus, right, particle. Now this particle is made up of an up quark and an anti-down quark. We don't really see these in nature, as they will appear in bubble chambers or particle detectors and then decay quickly. Okay, but initially when we were finding these particles, right, we would find, say, the pi plus particle, the pi zero particle, the kaon particle, plus and minus, the phi particle, and so on. And it took a while of work for physicists to determine this underlying symmetry that they're all made up of quarks. Specifically, mesons are made up of one quark and an anti-quark. Now, baryons are made up of three quarks. So yes, protons and neutrons are baryons. A proton is made up of two up quarks and a down quark, and a neutron is made up of two down quarks and an up quark. All right, next we have baryons. So baryons are made up of three quarks. So here you have our proton, which is two ups and a down, and a neutron, which is one up and two downs. You also have a lot of other baryons. Again, these ones are not stable in nature like protons and neutrons are, like the sigma plus, which are two up and a strange. So quarks are fundamental particles. If we go back up here, here are all in purple are quarks. Now our up and down quarks are the most important for us because they're the ones that make up everything we know in nature, right? All our protons and neutrons and everything that makes up those atoms, our periodic table, and so on. But quarks do have heavier cousins, which are identical, except they're slightly heavier. So we have the charm and the strange quark, and then we have the top and the bottom quark. And we can mix them up in similar ways, like here we have an up, a down, and a strange, gives us a sigma zero. Okay, so these are our quarks, and how we combine quarks is how we get all those different particles. Now initially we didn't know about quarks. When physicists were smashing particles together, what they saw were all of these. Okay, like the sigma and the pion, all of these ones I've been talking to you about. There's the proton and there's the neutron. And they had to come up with this pattern. And well, here's the pattern they came up with, right? These three patterns which organized these particles by their properties. A similar way we organize the periodic table of elements by the properties of those elements. Okay, and this pattern led to an underlying symmetry that all of these are made up of quarks, 6 quarks, 12 obviously if you count their antiparticles. And then we have leptons. Now the electron is quite amazing. We discovered it quite a long time ago, and as far as we still know, it is a fundamental particle of nature. And then we have this electron neutrino, or the neutrino, which we've talked about in grade 11 when we did particle decays, right? Radioactive decays. And we'd always have that neutrino coming out in our equations. These also have heavier cousins. Right? Again, not as stable in nature, but otherwise identical, other than they're heavier. So we have the muon and the muon neutrino. Muons are an interesting research for a lot of physicists who are looking at muons which come from space hitting our atmospheres, and they predict a lot less than what we're seeing. So a lot of physicists are trying to figure out where are all these extra muons coming from. And then we have the tau and the tau neutrino. Okay, so those are all of our All right, next thing you can see on our standard model of fundamental particles are bosons. Now, bosons are, we can call them messenger particles. Okay, they carry the information for our fundamental forces. So you have the strong force, the electromagnetic force, and the weak force. Not gravity, it's not a force, remember? So there is no particle, there's no boson which conveys the information for a gravitational force because it's not really a force. Okay, but the gluon will transfer the information for the strong force. The photon will transfer the information for the electromagnetic force, and the Z and W bosons transfer the information for the weak force. So what do I mean by when I say transfer the information? You'll see this more when we go down below and we talk about Feynman diagrams, and there's actually a great video that I'll show you from PBS Spacetime. But think of it like this. Here you have, this one's hard to see. Let's say you have a proton and another proton, or just two positively charged particles. Stay simple. Two positively charged particles. Now the electromagnetic force says these should repel. Right? Like charges repel. But where does that information come from? How does that information get conveyed? So what happens is you will have, say, this little particle, this. Okay, so this will be our photon. We'll leave this one and move to this one. Transfers the information, and so this one repels. And then it sends the photon back, transfer the information, repels, transfers, repels, transfers, repels. And this just keeps going back and forth, transferring the information. Now these are also called virtual particles because you cannot directly observe them. Okay, you can only see them indirectly. And the video will show you a little bit more about virtual particles. Okay, so moving on, we're going to look at Feynman diagrams, and I'm going to show you a video for Feynman diagrams. But basically, Feynman diagrams are a way of understanding how fundamental particles interact with each other. And of course, quantum mechanics allows for an infinite number of interactions, which can make things extremely complicated. That's why Richard Feynman is an amazing physicist and also an amazing teacher. If you ever go look up the Feynman lectures, came up with these Feynman diagrams to help simplify the problem to look at what interactions are most probable of those infinite numbers. Okay, so we're going to watch a video on Feynman diagrams, and then your challenge will be this challenge question, which I asked you to do for tomorrow, which is the same that's in the video.